All right, today we're jumping into one of the most fundamental concepts in all of mathematics, the matrix. Now, on the surface, it looks like just a simple box of numbers, but believe me, it unlocks some of the most powerful ideas in modern science and technology.
So let's kick things off with a big question, one that mathematicians wrestled with for a long time. How do you take something complex, like twisting, stretching, or flipping an entire space, and describe it using simple, predictable math? As we're about to see, the answer is just incredibly elegant.
So here's our game plan. We're going to start with the absolute basics, what a matrix even is. Then we'll check out the different types. After that, we'll get into the rules of how they work together, uncover their amazing connection to geometry, and finally, look at all the incredible places they show up in the real world.
Okay, first things first. Before we can get to all the cool stuff they can do, we have to be super clear on what exactly we're talking about.
At its most basic level, a matrix is really just an organized grid of numbers. Seriously, that's it. You can think of it like a spreadsheet, but designed specifically for doing powerful mathematics. It's all about holding data in a structured way. And here's what that looks like in practice. See those horizontal lines of numbers? We call those rows. And the vertical ones, yep, those are columns. So the size, or what we call the dimension, is just rows by columns. This one here has 2 rows and 3 columns, so we call it a 2 by 3 matrix. Now this notation is absolutely key. It gives us a precise address for every single number inside that grid. The little I tells you the row and the J tells you the column, so you always know its dimensions and exactly where to find any single element.
Okay, so now that we've got the basic definition down, let's explore the different flavors they come in. Because trust me, not all matrices are created equal. Their shape and what's inside them totally define what they can do.
This table here breaks down the most common types. A square matrix is a big deal. It has the same number of rows as columns, which gives it all sorts of special powers. Then you've got matrices with just 1 row or 1 column. We often call those vectors, and you can think of them as representing a single point or even a direction in space.
And within that family of square matrices, there are some real superstars. The most important one is the identity matrix. See how it has 1s running down the main diagonal and 0s everywhere else? As we'll find out in a bit, it acts just like the number 1 does in the world of matrix multiplication. All right, we know what they look like. Now for the fun part. How do we actually play with them? Let's get into the rules of the game, the algebra of matrices.
The good news is some of the basics are super intuitive. If you want to add or subtract 2 matrices, they just have to be the exact same size, and you just add the numbers that are in the same spots. Easy. And for scalar multiplication, you just take a single number and multiply every single entry in the matrix by it.
But multiplication, this is where things get really interesting and way more powerful. There's one crucial rule you absolutely have to remember. The inner dimensions must match. That means the number of columns in the first matrix has to equal the number of rows in the second.
So how does it actually work? Well, to get just a single entry in the new matrix, you perform something called a dot product. You take an entire row from the first matrix and an entire column from the second. You multiply their corresponding elements 1 by 1, and then you add all of those products up. You repeat that process for every single spot in the final matrix.
And this brings us to one of the biggest, and I mean biggest, things you have to get used to in linear algebra. The order matters. With regular numbers, 2 times 3 is the same as 3 times 2, right? Well, with matrices, AB is almost never the same as BA. Swapping them can give you a totally different result, or sometimes it won't even work at all.
So you're probably wondering, why is multiplication so weird? Well, there's a beautiful geometric reason behind it all, and this right here is where it all starts to click.
I want you to stop thinking of a matrix as just a static box of numbers. I want you to think of it as a machine, a transformation machine. You feed it a point represented by a vector, and it spits out a new, transformed version of that point.
For instance, take this specific matrix right here. It might just look like some numbers, but it actually contains the secret code for a rotation. If you multiply the coordinates of any point by this matrix, the result is that point rotated perfectly around the center. It's a direct link between abstract numbers and physical movement.
And what about this one? This matrix acts like a universal zoom control. Multiplying a vector by it scales everything up or down, stretching or shrinking the entire coordinate plane from the origin.
Here, you can see how just a simple arrangement of positive and negative ones inside a matrix can perform a perfect reflection, flipping everything across an axis like a mirror.
And for our last trick, a shear. This matrix can actually slant the entire grid, turning nice neat squares into slanted parallelograms. So the huge takeaway here is that all these complex geometric actions, rotating, scaling, reflecting, are all just matrix multiplication at work under the hood.
And that deep connection to transformations is exactly why matrices aren't just some mathematical curiosity. No, they are literally everywhere, running silently in the background of our modern world.
I mean it. Matrices are the absolute backbone of modern technology. The incredible 3D graphics you see in movies and video games, that's all matrices, rotating and scaling objects. They're at the core of quantum mechanics, describing particle states, and they are the engine behind the AI and machine learning algorithms that are changing our world.
Okay, let's bring it all home and wrap up the core idea we've uncovered about these incredible mathematical objects.
We've seen that a matrix is more than just numbers. It's a language. It's a powerful way to describe systems and transformations. This simple idea of just putting numbers in a grid opens the door to incredibly advanced concepts like eigenvalues and beyond. Which really makes you wonder, doesn't it? What other secrets are just waiting to be discovered inside these simple arrays of numbers?